Hi students, welcome to all of you to this concepts and snippets session. This session focuses on the major area in a particular chapter. Today we are going to discuss structure of atom, and I am going to give you a focus on hydrogen spectrum. It is called line spectrum. You know, Rutherford proposed his planetary atom model. It was unable to explain stability of an atom. So Bohr proposed his quantization of energy model. Okay. The major developments that led to Bohr atom model is Max Planck's quantum theory of radiation. According to Max Planck's quantum theory of radiation, energy is emitted or absorbed by a body not continuously but discontinuously in the form of small packets of energy called quanta. Thus, energy of a quantum of radiation is given by Max Planck's equation E equal to h nu, where E is the energy of a quantum of radiation in joule, h is Planck's constant 6.626 into 10 to the power of minus 34 joule second, and nu is frequency of radiation in second inverse or in hertz. Now, let us discuss hydrogen spectrum. Bohr model is highly successful in explaining the formation of different sets of lines in hydrogen spectrum, also in hydrogen-like species. Hydrogen-like species means one electron systems like helium plus ion. A singly charged helium plus ion has one electron like hydrogen, but the nuclear charge is 2. Again, you have lithium 2 plus ion, doubly charged lithium ion, but the nuclear charge is 3. Thus, let us see the different sets of lines which appear in hydrogen spectrum. One of the biggest advantage of or merit of Bohr model is he was able to calculate the wave number of the different sets of lines using Rydberg equation. The calculated values are in very much agreement with the experimentally determined values. Okay, let us see the hydrogen spectrum. Okay, I have included a problem also so that you can work out. The question is, calculate the frequency of spectral line emitted when the electron in third energy level in hydrogen atom de-excites to ground state. That means electron after reaching the third energy level returns to the ground level. As you know, ground level has the lowest energy, so the electron will be stable. The high energy levels are called excited level, so stability is less. So, as the electron returns to the different lower levels, you get different series of lines. Thus, any transition from higher level to ground level, that is the first level, the line is called Lyman series. It appears in the ultraviolet region. So, we need a spectrometer to watch the lines. So, Lyman series is the first set of lines in hydrogen spectrum when electron from any higher level returns to ground level, that is first shell. The second set of lines are called Balmer lines. Balmer lines, the important feature is these lines appear in the visible region. So you can see with our naked eyes, these lines have different colors depending upon the energy that is released. Balmer lines are the visible lines in hydrogen spectrum. Okay. So for any transition from a higher level to the second level, the set of lines are called Balmer lines. Okay. Remember, the line that appears when electron from third level to the second level, it is called the first line of Balmer lines or the first line of Balmer series. It is called H alpha line. Okay. So H alpha line, it is called the first line of Balmer series of hydrogen. H line of Balmer series. Alpha line of Balmer series means the spectral line for the transition, spectral line for the transition third level to the second level. So, for all Balmer series, the electron returns to the second level. If it is from the third level to the second level, we call it as the first line of Balmer series. Okay. Similarly, you have the Paschen series. Paschen series are a group of lines appear when electron from any higher level returns to third level and so on. Thus, we have the 5 series of lines, each correspond to a definite transition. It shows what? Energy of an electron in an atom is quantized. Electron can have only definite values. Electron cannot have any arbitrary value. Okay? Bohr very clearly found out energy of an electron remains constant as long as it remains in the same major energy level. Energy changes only when electron jumps from lower level to higher level, or energy is emitted when electron returns from higher level to lower level. So, a spectrum is a record of energy emission occurring when electron from higher level returns to the lower level. It is called line spectra because each transition corresponds to a sharp line. Okay. So, spectrum or atomic spectrum is line spectrum. Okay. Now, look at this problem. Another important point you have to remember is, suppose an electron from the infinity level returns to any of the ground level, that line has the highest wave number or highest frequency. That line is called limiting line. I repeat, limiting line is the spectral line that appears when electron from infinity returns to a lower level. For example, an electron from infinity returns to ground level, that is n equal to 1. It is the limiting line of Lyman series of hydrogen or for that particular species. Suppose electron from infinity returns to the second level, it is the limiting line of Balmer series of hydrogen and so on. So, a limiting line is the spectral line that appears for the transition of electron from infinity to a particular lower level. Remember, it is the line having the highest or maximum wave number or frequency. Clear now? So, when hydrogen gas is taken in a discharge tube and the potential is applied gradually, so that the electron from the ground level, that is in the K shell, it get excited to the different higher energy levels. These higher energy levels are unstable. So, electron returns to the lower level. The difference in energy is given out in the form of radiation that can be recorded and that can appear as a spectrum. In hydrogen spectrum, we have 5 sets of lines. Okay, each sets of lines indicate a particular transition. Another thing you have to watch is, you see the energy level arrangement. As you go to the higher level, the energy spacing is smaller and smaller. The largest energy difference is between the first level and the second energy level. From second to third, energy difference is less. From third to fourth, energy difference is still lesser. And as you go to higher level, energy levels are closely spaced. So remember, in an atom, energy levels are closely spaced as you move to higher and higher energy level. The maximum energy difference is between energy level 1 and energy level 2. The second energy level is sometimes called first excited state, because ground level is n equal to 1, So second level will be the first excited level. Okay. Now the frequency of spectral line for this particular transition from the third level to ground state. That means it is Lyman series. 2 to 1 means the first line of Lyman series. 3 to 1 means it is the second line of Lyman series. Okay. Now, how will you find out frequency? Nu. It is C by lambda. Nu equal to C by lambda. 1 by lambda is nu bar. So, you have the equation. Okay. The transition from third level to the ground level correspond to the second line of Lyman series. Hope it is clear. That's why I have taken the spectrum as such. So you can easily see. See 2 to 1, the first line of Lyman series. 3 to 2, the second line of Lyman series. This appear in the UV region. That's very important. All Lyman series appear in the UV region, ultraviolet. So we cannot see with our naked eye. You need a spectrometer. Whereas Balmer lines can be easily visible. Okay. Now, you are asked to find out the frequency. Nu equal to C by lambda. That's the formula. Where C is velocity of light, lambda is the wavelength, and 1 by lambda is wave number. Okay. And 1 by lambda is wave number. So we have the Rydberg formula to calculate the wave number. So when you multiply with the velocity of light, you can find out the frequency. Okay. Therefore, frequency equal to C nu bar. Okay. That is equal to nu bar, Rydberg constant RH into Z square into 1 by N1 square minus 1 by N2 square. So, substituting the velocity of light, so 3 into 10 to the power of 8 meter per second into Rydberg constant, let it be 10 raised to 7. For calculation, we take it as 10 raised to 7 into atomic number square divided by 1 by N1 square minus 1 by N2 square. That much second inverse. That is the frequency. Now, N1 is the ground level, N2, the higher level, is third level. Therefore, what is the frequency? It is, 3 into 10 raised to 15. Okay. For hydrogen, it is atomic number 1 square, into the ground level is 1 square, the upper level is 3, so 3 square. That much second inverse. Okay. Therefore, the frequency of spectral line, the frequency of spectral line for the transition 3 to 1 in hydrogen atom is frequency equal to 3 into 10 to the power of 15 into, it is 1 by 1 square minus 1 by 3 square. Okay. That means second inverse or hertz. It is 9. So 9 minus 1, 8. 8 by 9. So 3 into 10 to the power of 15 into 8 by 9 second inverse, or it is 3. It is 8 by 3, or it comes to be 2.66 into 10 to the power of 15 second inverse. Okay. Such problems are very frequently asked for competitive exams like NEET or G mains. So you should be familiar with how to calculate. Suppose it is helium ion. For helium ion is hydrogen-like. The only difference is what? Rydberg equation is same, but Z square value changes. Okay. So note. For the same transition in hydrogen-like species, that is helium plus with atomic number 2 or lithium 2 plus with atomic number 3 or beryllium 3 plus with atomic number 4, we have to include Z square in the Rydberg formula. That's why whenever we write Rydberg equation, we write Z square. You see, we write the Z square, it is to include the atomic number of the species. Thus, you have the frequency like this. Okay. So, suppose you want to calculate for this hydrogen-like species for the same transition, what is the frequency? You multiply with Z square. That's what. Okay. For the same transition, in helium plus ion. Okay. So, the frequency for the same transition in helium plus ion. See, remember, such questions are always asked for NEET. A particular transition in hydrogen spectrum is given. The wave number also will be given or the frequency will be given. What is the corresponding frequency for the same transition of helium plus or lithium 2 plus? The only thing is you multiply with Z square. Okay. So, the frequency is, okay. So, frequency of helium plus ion for the transition 3 to 1, it is Z square into frequency of hydrogen for the same transition, or it is equal to, therefore, frequency of helium plus for the transition equal to Z square, that is 2 square into 2.66 into 10 to the power of 15 second inverse, or it is 10.64 into 10 to the power of 15 second inverse, or it is 1.064 into 10 to the power of 16 second inverse. Such spectrum related questions are very, very important in atomic structure. Okay. So, we will be doing similar questions, a number of questions from atomic structure. Right. Thank you.